Howdy. Welcome to the second lecture in Module 3 of Geography 660 Applications in GIS. This is the second lecture on geodesy, and it is going to deal with topics of the geoid, ellipsoid, and datums. The learning objectives for the submodule include describing the shape of the Earth, describing difference between a sphere, an ellipsoid, and the geoid, describing what is meant by a datum, both horizontal and vertical datums, in fact, and finally, giving an overview of the history of how our understanding of the Earth's shape has changed, and I hope giving you an appreciation of this history. Not surprisingly, the actual shape of the Earth is quite complicated, and it is not practical to mathematically describe the Earth's entire topographical surface. It is, however, possible to obtain mathematical models that really approximate what we would consider as the Earth's mean sea level surface. And if you work on vertical datums, there's a whole issue about what is mean sea level defined, but what I'm going to try to get across to you in this lecture is using this concept of mean sea level to kind of describe the shape of the Earth. And as we'll talk today, there are several models of varying complexity that we can use depending on what our application is. The first thing I should say is the actual shape of the Earth is what we call the geoid, which literally means Earth-shaped, so not surprising, the shape of the Earth is the geoid. And for our purposes today, we can take the geoid as representing, again, this Earth's mean sea level surface. And I think on the oceans, everyone can kind of imagine what a mean sea level surface might sort of represent. On land, you could imagine this as kind of if we had a well that was magically connected to the ocean, and water in that well would rise up to the Earth's mean sea level. Or I guess the other thing you can imagine, we're in some future world like the horrible movie Waterworld, and then we have, except for a few little places, we have the Earth's mean sea level represented. But it's the concept I'm trying to get across, and I'm going to delve a little bit more detail in describing that in a second. To be more precise, the geoid of the Earth is represented by what we call an equipotential gravimetric surface. And really what this means is that if you would put a marble on this gravitational equipotential surface representing the geoid, gravity everywhere on that surface is the same, and the marble would have no reason to move anywhere because the pull of gravity is the same everywhere on this surface. If I would take that marble and I would move it up and down, it would require me to, moving it up would require me to expend energy. And what you need to take away from this is, although the measurement of little g is the same everywhere on this equipotential gravimetric surface, the distance from the mass center of the Earth to this equipotential surface differs over the Earth. It differs because of a function of the composition of the Earth and other things. So the distance from the mass center of the Earth to this equipotential gravimetric surface describing the geoid changes. And you're going, okay, what does this really mean? So this means the geoid really kind of looks like a lumpy potato. And it has undulations from the ellipsoid, which we're going to describe in a few minutes, as much as 100 or so meters, actually. as much as 100 meters. There's also a rather large bulge in the Earth of about 10 to 15 meters in the southern hemisphere, and sometimes this causes people to describe the Earth as kind of pear-shaped, a little bit larger in the southern hemisphere than in the northern hemisphere. So we have this surface with undulations of about 100 meters in the geoid. And one of the things you should know is as our technology has increased, our ability to understand the gravipotentiometric surface, the equipotential surface, this geoid has improved tremendously. So this is just a highly, highly exaggerated figure from your textbook showing the Earth, the geoid, is actually this lumpy potato with highs and lows in it. And again, the distance from these highs and lows is, on the order of 100 meters. This is a slightly older figure. It describes the geoid heights. These are the heights relative to an ellipsoid. In fact, the ellipsoid that's historically been used in GPS measurements, the WGS-84 ellipsoids. And you can see that the lows are on the order of maybe 100 meters below ellipsoid heights. The highs are on the order of maybe 70 meters above the ellipsoid. So this is kind of the overall gross shape, not gross, the geoid, the actual shape of the Earth. And as I was saying, as technology improves, we can have better and better understanding of what the actual shape of the geoid is. And not only does our knowledge of the geoid improve, but as our ability with global navigation satellite systems to precisely know our positions, we actually require better and better geoids because our ability to measure things is improving as well. So this is a current geoid model for the United States, produced by NOAA. And you can see the various geoid heights, but you can understand that what is leading to these undulations in the Earth is really due largely to the underlying geology and density of the Earth material beneath you. Now, if you're doing certain applications, understanding the shape of the Earth to the level of the geoid is important. However, while you can represent the geoid mathematically, it's simpler than the Earth's topography, the Earth's topographic system, it's still very complicated to represent mathematically. Basically, you have to do it in spherical coordinates, and it can be quite complicated. So for most uses in cartography and GIS, we use a simpler representation of the shape of the Earth. And this is what we call the ellipsoid. Some people will call it a spheroid, but the term ellipsoid is preferred. We can define an ellipse or an ellipsoid by two measurements. The first is the semi-major axis, which is the equatorial radius, and the second is the semi-minor axis, which is parallel to the rotational axis of the Earth. You can define a flattening ratio as the difference between the semi-major and the semi-minor axis divided by the length of the semi-major axis. As we'll talk a little bit about in a few more minutes, for the Earth, A typically is bigger than B. Not typically, A is bigger than B. Now, what we try to do with our ellipsoids is we define our ellipsoids where we try to fit the ellipsoid to the geoid, and that is what this illustration is trying to show. You must remember, however, that one ellipsoid that may fit one portion of the Earth quite well may not fit another. So on this, there are some locations where they pretty much coincide. There are some others where they don't. And hence, for one place on the Earth, the best fitting ellipsoid may be different than the best fitting ellipsoid for another portion of the Earth. And this has led to the use of multiple ellipsoids to be used for surveying purposes in different portions of the Earth. Also, as our understanding of the actual shape of the Earth, the geoid, has improved, ellipsoids have been modified, or new ellipsoids have been used to take this new information into account. Your textbook, the Bolstoid textbook, has a number of illustrations that really illustrate this. So for example, it's showing the geoid in this figure as the thick gray line. And you can see that the best local ellipsoid A fits well in some places, whereas the best local ellipsoid B fits better in other places. So this leads to the idea that an ellipsoid you may pick for mapping in North America may be different than an ellipsoid you may select to represent Japan, for example. And that is the case. There are a number of illustrations that we can draw upon to kind of try to show us the relationship between these different Earth surfaces. This is a classic one, come from the 1990s from Peter Dana. And by the way, you'll notice over the next few lectures that there are a number of illustrations I'm using from Peter Dana. He had developed early on some very nice websites in terms of GPS and datums and map projections, and he was actually a lecturer in geography and GIS at the University of Texas. So some of his examples are apropos to a Texas-based GIS program. So what this is trying to show is the undulations of the Earth's topographic surface in green, the smoother geoid surface, but that's still complicated, and then a best fitting ellipsoid to the geoid. So remember, what the geoid does not represent all the complexity of the topographic surface of the Earth. It represents these longer scale undulations in the Earth's gravity field, in essence. That's not quite right. It represents longer undulations in the Earth's surface, and then we try to fit an ellipsoid to it. This is a slightly more complicated diagram showing the same thing. We're showing the terrain, the geoid, the even smoother Earth's mean sea level surface. I've been using the mean sea level surface and the geoid synonymously. There are differences that go beyond the scope of this class. And then what's most important is the best fitting ellipsoid. And what this also tries to show you is that in some places they correspond, in other places they diverge. And in some places the terrain is above the ellipsoid, and in some places the terrain is below the ellipsoid, as well as the geoid, etc. So just useful for you to contemplate things for a second. This figure comes from your textbook, and I think you should spend a little bit of time going over it because it defines a very important relationship that you will come across as a GIS professional. And it shows the relationship between different heights: the ellipsoidal height, the orthometric height, and the geoidal height. So historically, elevations listed on most topographic maps are orthometric heights. Heights that are recorded by modern day GNSS or GPS instruments are typically ellipsoidal heights. So if you're using elevation information, you need to be aware whether or not you're receiving it as an orthometric height or as an ellipsoidal height. And in essence, the ellipsoidal height, little h, is the elevation of the Earth's surface above or below the ellipsoid. And again, it's whatever ellipsoid you're employing for those measurements. And typically with GPS, again, it's been one we'll talk about, WGS 84. The orthometric height is the height of the Earth's surface above or below the geoid, big H. And in order to relate the two together, you need to know what the geoidal height at your location is. And the geoidal height is the height of the geoid above or below the ellipsoid you're using. And it is possible to get all those bits of information, but you need to understand the relationship between ellipsoidal heights, orthometric heights, and geoid heights, because at some point in your professional career you're probably going to have to convert between those. Again, modern day GNSS equipment will often give you ellipsoidal heights. Topographic maps have historically been orthometric heights. So, that was a very brief introduction into the shape of the Earth. Your textbook and other ancillary information is available on the course site can give you a deeper dive into those topics than I can in my few minutes I have in terms of lecture here. But this brings us to the concept of a datum. And before I go any farther, I will state that I am approaching this as a geographer, which is at a much broader level or much more generalized level than you might approach understanding a datum if you were a surveyor, for example. So just trying to tell you that there's much more information and much more complexity potentially in datums than I am going to present to you in the next few minutes. But I'm going to try to give you kind of a pragmatic overall description of this. So in surveying and geodesy, and by the way, geodesy is kind of the science that deals with the shape and measurements on the Earth. A datum is a reference point or surface against which position measurements are made, and an associated model of the shape of the Earth for computing positions. And that's a Wikipedia definition. There are other definitions out there, but this is a good place to start from. So, a geodetic datum is a mathematical model of the Earth upon which geodetic computations are based. A datum is a reference system that has two components. The first is it has a specified ellipsoid with a spherical coordinate system and an origin. And it also will typically or historically has had a set of highly accurate surveyed points and lines which are related to this. And there are kind of in use today both regional and global datums, and I'm going to describe both of those to you today. Much of what you will come across are regional datums. And a regional datum is fitted and intended for use in a specific area. And there are a couple of regional datums that are commonly used in the United States today. Within a geodetic datum, there's a number of different elements. there's a description of the ellipsoid, and those are encompassed by the semi-major and semi-minor axis details. The other thing that a geodetic datum has is it has a latitude and longitude very precisely determined for really what is called the tie point of that regional datum. The description of a regional datum also has an azimuth from the initial point to another point, typically the second point in the survey. Another assumption is, and I don't think this is always met in all datums, but it assumes the ellipsoid and geoid are coincident at that tie point. That means that the ellipsoid and geoid are the same elevation, or the same distance from the center of the Earth, and the Earth's spin is parallel to the ellipsoid's minor axis. And here is an example of a regional geodetic datum, one that was in common use in the United States for a long time, and we'll talk about this one in more detail later. But this is an example. This is North American datum of 1927, which is typically referred to as NAD 27. It is based on the Clark spheroid of 1866, which is a common ellipsoid that was widely used. You can read the semi-major and semi-minor axes there. Those are the actual A and B. The origin or tie point for NAD 27 is a very important location in surveying history of the United States. It's Meade Ranch, Kansas, U.S. And its latitude and longitude, which are listed here in degrees, minutes, seconds, are very precisely determined, even to much greater precision than I'm representing on this slide. And the angle there is the angle in that survey to the second survey station in the NAD 27, which is Waldo. And just a little history, if you do not believe me that this is important. So if you can drive through Kansas, like I do on my way to see my parents in Iowa, you can come across this signage that talks about the Geodetic Center of North America. And I love this. This is Kansas. So it says on a ranch 18 miles southeast of this marker, there's a bronze plate. And it talks about that this is a primary survey station for the North American surveys we're going to talk about. And it was located in 1901 by the U.S. Coast and Geodetic Survey, which no longer exists. And it's at Meade Ranch, Kansas. And there, in fact, is a surveyor standing on the tie point that is the heart of NAD 27 survey. And lest you believe me that this is not important, I would point out that there's companies out there that will sell you replicates of that survey marker, so you can buy one for yourself. There's the Meade Ranch one. It says it was surveyed in 1891 initially. I will also point out that, again, because I work in the Antarctic, there's an equivalent Antarctic survey marker. And notice that this is from January 1st, 2000. Unlike Meade Ranch, Kansas, which is on bedrock, or I shouldn't say on bedrock, I actually don't know because I've never been there, but it's on the stable platform, geologically speaking, of North America. The geographic South Pole is on an ice sheet, and the survey marker of the South Pole will move several meters every year, which requires somebody to come back and survey it every year. So that's a pretty good job. You got to go to the South Pole and re-put in the new survey marker. And hence every year they have a new survey marker. The one from January 2000, which I actually have a copy of, I know the person who actually created that. She worked at the South Pole as a communications officer for a while. So it's kind of cool to know the people who go in every year and actually put in and survey in the geographic South Pole. But the point being, there's one of these bronze markers that marks the beginning point of the NAD 27 and later NAD 83 regional datums that are used in the United States. And we'll talk more about those in subsequent lectures. These regional datums that exist for nearly every country on Earth were developed for pragmatic, practical surveying purposes. There are also things that are called global geodetic datums. And in this case, the reference ellipsoid is chosen not to be the best fit for one particular region on Earth, but the best fit globally. Rather than having a tie point, the center of the datum is actually their center of mass. And the reason we need these global geodetic datums is that we can then relate accurately points on any continent throughout the world that are tied through this global datum. And these global geodetic datums, because they deal with satellites and other things, they need to account for Earth's gravitational attraction and centrifugal acceleration and a lot of other things about the Earth. There's a number of these that have come into existence as technologies for understanding the relationship on one point on the Earth to another a continent away have improved. There was the Geodetic Reference System of 1967, the World Geodetic System of 1972, the Geodetic Reference System of 1980, and the one that's most commonly in use today is the World Reference System of 1984, often referred to as WGS 84. And again, this is the basis of measurements with GPS system today. Now, one thing you have to realize is that regional geodetic datums were developed to help us survey countries. And obviously in surveying, there's both errors in some of the measurements, but also over time, our technology has improved. And so both in determining the positions of various locations in the survey, but also in our ability to understand the exact shape of the Earth. And so what happens is once we have a significant large number of points, we sometimes need to, in essence, go harmonize these and improve the locations. Now, what this means is that in most cases, not the actual locations of these points have changed. The location of the points on the Earth have not changed. Our knowledge of the locations has improved. And so, over time, these datum adjustments mean that a surveyed point, its latitude and longitude may be slightly adjusted. And this adjustment will impact all the points that have been collected up to a particular point in time. And I'm going to add a caveat here, which as our ability to measure becomes more important, there are actually places on Earth, think California, where you survey something in because of tectonic activity, it actually does move. Now, for some applications, like my using global satellites with 500-meter footprints, that might not be important. But for precise surveying, these things do matter. And we can now actually measure millimeter changes in plates and other things. So just remember, That's a tangent. But remember that because of various factors, our knowledge of the positions of points on Earth has changed, typically improved. And what we do is we do these datum adjustments that take this into account, but it means that the positions of the points in terms of their latitude and longitude change. It doesn't mean they've moved physically on Earth. And basically these adjustments result in a series of datum that each is better and more accurate than its predecessor. And it's typically accomplished using a large least squares adjustment that changes the coordinates of all existing datum points. But again, the point to remember here is the points do not move, but our estimates of their coordinates will change. And think about it. If our understanding when we made that original survey of the Meads Ranch, Kansas tie point, which goes back, and every other thing that was surveyed based on that is based on that. And if our knowledge of the position has improved since it was put in the late 1890s, then every other position that was based on that one tie point, which is millions of points, all of a sudden gets adjusted a little bit too. That makes sense to everybody? Therefore, one of the things you need to remember is that we cannot necessarily just say the North American datum of 1983 or NAD 83. That's no longer sufficient in describing a datum. You actually have to put the adjustment year. And there are a number of geodetic networks that are out there. The High Precision Geodetic Network, HARS, and these are sometimes used in the adjustments. So, for example, there's an NAD 83 CORS 96, which incorporated adjustments from the continuing operating reference station. So just beware that these adjustments happen, and they're actually happening, my understanding, a bit more frequently now. And with each adjustment, the positions change a little bit. Another thing we need to talk a little bit about is that there are actually two measurements of a foot out there. You just should be aware of this. What most people are aware of is this thing called an international foot, and you can see how it's abbreviated. And one international foot is exactly 0.3048 meters. And that's a good conversion to remember in your brain. And the international foot was adopted as a standard in the 1950s. However, you need to be aware that the slightly longer metric to foot conversion of the U.S. survey foot, that's the one that's at the top, the U.S. survey foot, where 1 meter is 39.97 inches, or you can look at that longer conversion factor. This is what is used to convert between feet and meters among geodetic coordinate systems within the United States. So just be aware, this is a little tidbit out there, that although most conversions use the international foot, you need to use the slightly longer metric foot. You need to use the U.S. survey foot to convert between geodetic coordinate systems within the U.S. And you also have to trust that other people are using the correct one. Okay, so I've talked a little bit about datums, and I wish I could go into more detail, but I'm trying to keep this lecture rather short and having you do some additional readings. Well, here's why it matters. So this is another one of those figures from Peter Dana that really works well. So if you go to the Texas Capitol Dome in Austin, you can find a horizontal benchmark that has a location listed in light blue there in terms of its latitude and longitude in terms of WGS 84. If I take that same position, that same latitude and longitude, or that same position, and I translate it into different regional datums, that position will actually shift. And in some cases, you can see that it actually shifts by over 500 meters. Now, not surprisingly, some of those larger shifts are using datums that you would not apply in the United States. One of the things I do in my class is I give our students a position on campus in terms of a very precise latitude and longitude, have them put it into a GPS, and send them out with different datums. And what they find is that even though they have all started with the exact same latitude and longitude, that latitude and longitude puts them in a different position on campus. And you can be even selecting different versions of even using relatively similar is not the right word, even using commonly used datums like NAD 27 and NAD 83 will take that same position and you'll be off tens of meters. So it's an important thing to understand is that the same latitude and longitude, if you put that into a GPS, that same latitude and longitude in different coordinate systems puts you in an actual different physical position on the surface of the Earth. That's what this graph is trying to show. And by the way, this is the National Geodetic Survey Data Explorer, and it will point out the capital benchmark. And another thing I should just point out, that because the Earth is not a perfect sphere and the Earth is actually an ellipse, and the Earth is, as we'll talk a little bit about, is what we call an oblate spheroid. This means that the distance from the mass center of the Earth to a point on the equator is a little bit longer than the distance from the mass center of the Earth to a point at the North or South Pole. And one of the interesting things that this leads to, for example, is the fact that because the Earth is this oblate spheroid, it turns out that then, therefore, a point on the surface of the Earth near the equator is farther from the center of the Earth than a point at the poles. And one of the interesting things that this leads to is the fact that the mountain Chimborazo, which is in Ecuador, is actually the farthest point from the center of the Earth. So in some sense, Chimborazo, you can go walk. It's much easier to climb, by the way, to get to the top of Mount Chimborazo than it is to get to the top of Mount Everest. So if you climb to the top of Mount Chimborazo in Ecuador, you are actually farther from the center of the Earth than if you would go to the summit of Mount Everest. So save yourself tens of thousands of dollars and climb Chimborazo instead of Mount Everest, if you're into that sort of thing. So I'm going to finish this lecture by talking about a little bit about the history of the shape of the Earth. And I do this because I find it fascinating, and I hope you do as well. So we'll get into maybe a little bit about flat Earth, etc. But really, historically, people have known about the shape of the Earth for a long, long time. The first written description of the Earth as a sphere appears in a very important work. It appears in Plato's Phaedo, which was published written circa 380 BC. So for those of you who hope everyone is aware, Plato is a very famous philosopher, Greek philosopher, and Phaedo is Plato's fifth and last dialogue. And by the way, for those you might not be aware, Plato wrote his philosophy in these dialogues, which were written in the voice of his predecessor Socrates, or if you're a Bill and Ted follower, Socrates, right? Bill and Ted's Great Adventure, kind of a funny movie. But Plato's dialogues are dialogues of Socrates with other philosophers and people. And Phaedo is the fifth and last dialogue, and it actually, probably most famously within the Phaedo, it describes Socrates' death scene. And you might remember Socrates had to drink hemlock. And his last, he says, Crito, I owe you a cock. Or pardon me, he's talking to Crito. I owe a cock to my friend. Will you remember to pay the debt? But prior to the death scene in Phaedo, earlier in this dialogue, Socrates is talking to another philosopher, and he says, and I imagine that he would tell me first whether the earth is flat or round. My conviction is that the earth is a round body in the center of the heavens. So here is Plato circa 380 BC, in essence giving us the idea of a geocentric universe, one in which the earth is round and is at the center of the universe, or at least the center of the heavens. Not only that, if you go on to read this, he says, and I believe the earth is very vast, and that we who dwell in the region extending from the river Phasis to the Pillars of Hercules inhabit only a small portion about the sea. And basically he's saying those of us who dwell in the Mediterranean are only part of a much broader, much more vast planet. So that's 380 BC, right? It's not Christopher Columbus, which we'll get to in a minute maybe at the end. But the Greeks, circa 380, were already contemplating a geocentric round Earth, a geocentric universe with a round Earth at the center. Just a little bit later, 310 to 230 BC, was the first person who postulated that you might have a heliocentric universe rather than a geocentric one. And this is according to Archimedes, the person who got in the bathtub and realized water was displaced relative to your volume, among other things. According to Archimedes, the first person to postulate a heliocentric rather than geocentric view of the heavens was Aristocles, a Greek astronomer, and I mispronounced his name yet again, a Greek astronomer. And there's his statue at the university in Greece. So the Greeks not only knew that the earth was round, but they postulated, circa 300 BC, maybe a little bit later than that, 250 BC, that the earth was revolving around the sun. Probably most impressively, to me at least, was that circa 250 BC, the Greeks also knew very precisely how large the earth was. And this goes back to Eratosthenes, who was the head librarian at the library in Alexandria, Egypt, which at the time contained, the largest body of knowledge that the earth had ever seen. And he determined the circumference of the earth. And what always amazes me about this story is how he knew some of these facts. And it is all based on an observation that he, as this great librarian, some way knew. That on the summer solstice at high noon, that the sun was directly overhead at this town called Sen, which is now called Aswan. And it is in southern Egypt. It's where the Aswan High Dam is today. And he knew at the summer solstice, which of course for those of you who may remember is on the day of the summer solstice, the sun is as far north in its north and south transit over the course of the year. And you might also remember it's at 23.5 degrees north latitude. So at noon, at high noon, over the town we know as Aswan today, Sen in the past, you could look down a well and you could see the orb of the sun because it was directly overhead. So he knew at this particular date, at this particular time, the sun was directly overhead there. He also knew that at the same day, at high noon, in his own town of Alexandria, which is on the Nile River Delta on the Mediterranean, north of Aswan, he also knew that the sun would cast a shadow because it wasn't directly overhead. And there's some ambiguity, but he either put a stake in the ground or used a wall, and he realized that the angle that the shadow cast on Earth, and I'll show you a picture in a second, in Alexandria at that same time was about 7.5 degrees. And he also knew the distance between Sen and Alexandria, which allowed these things, knowing these things, allowed him to make a very precise calculation of the circumference of the earth. And here's my rendition of it. There's a number you can find, and some of the numbers you will notice there's a little bit of ambiguity about. But you can see at Sen at 23.5 degrees north latitude, the sun is directly overhead. His pole at Alexandria, notice I'm using 7.2 here. I've seen 7.2 and 7.5. He knows that that is a shadow that it's casting. And then he also knew, because the Greeks were great at geometry, that you can do complementary angles. You might remember from your high school geometry. So if that's angle 1, then the complementary angle, angle 2, is going to be the same thing. So he knew that, in essence, the angular distance between Sen and Alexandria was 7.2, 7.5 degrees. They also knew that, well, if you know that a circle has 360 degrees in it, that's about 1/50th of a circle. He also knew the distance on the ground was about 805 kilometers between Alexandria and Sen. And if you do that calculation, that, that 7.2 or that 805 kilometers is 1/50th of the circumference of the earth, then you would know that the circumference of the earth, by his calculation, was 40,250 kilometers. Now, at the bottom of this slide, you can see my modern calculation of the circumference of the earth using the radius of the earth from the WGS 84 ellipsoid, which is, well, you can see a little over 6,000 kilometers. And if you do the math, circumference is 2 pi r, you come up with 40,075 kilometers. So 250 BC, the Greeks not only knew the earth was round, was revolving around the sun, they knew the circumference of the earth to within a few percentage correctly. Oh, but Columbus was the only one who knew the earth was round in the Middle Ages, right? That's the myth. But no, the Greeks really knew what was going on. Now, So the Greeks knew the earth was round. It wasn't until much later, 1600s, when a few people postulated the earth was not a perfect sphere. And Isaac Newton and his compatriot Christian Huygens recognized that the gravitational theories of Isaac Newton required that the earth would be flattened at the poles. Because again, remember, they viewed the earth as spinning around. They realized that gravity would push out the equatorial regions a little bit relative to the poles. They described the earth as this oblate spheroid, where the semi-major axis is a bit longer than the semi-minor axis. So these were the theory of the shape of the earth based on Newton's gravitational theory. Well, starting in the 1660s, two Frenchmen Abbé Jean Picard and Jean-Dominique Cassini, decided to test this. And modern scientific surveying really got its start in France, in part because the expensive habits of the French aristocracy required good taxation, and good taxation required good maps. So the French started good surveying. So in the 1660s, they went out to test this. And what they did was they very precisely surveyed the length of arc at two locations along the Meridian de Paris. And the Meridian de Paris was the prime meridian the French were using, because the French would never use the prime meridian that the British were using, right? So what they did was basically they measured a certain amount of distance. I'll show you a figure in a minute. But their surveying suggested the opposite. Their surveying suggested that the Earth was actually a prolate spheroid, that it was actually the distance, the semi-minor axis, that B, was a little bit bigger than A. And just a couple of pictures to put this into some perspective. So there's Sir Isaac Newton, there's Christopher Huygens, the theorist who thought the Earth was an oblate spheroid. There are the two Frenchmen, Jean-Dominique Cassini and Jean-Philippe Picard, who were the empiricists, the surveyors, measuring and trying to determine if the empirical data fit the model. And by the way, there is the apple tree, so everyone knows that Sir Isaac Newton, had this apple fall on him, and he came up with his theory of gravity. By the way, I took this picture at Cambridge University, where Sir Isaac Newton had an office, and in fact, if you would spin around 180 degrees from the tree, you would actually look into his office. So that is, an apple tree in commemoration of Sir Isaac Newton. It's probably not the apple tree, but a little bit of history. And I would also point out, some of you may have already guessed this already, but Captain Jean-Luc Picard of Star Trek The Next Generation, played by Patrick Stewart, was actually named for Jean-Philippe Picard. So Star Trek, in a number of things, has actually made an homage to earlier scientists. It's kind of cool. But back to our story. So Newton and Huygens' view of the world was the Earth is this oblate spheroid. And that centrifugal force, just like in the center tube, is pushing the equator farther from the center of the Earth than the poles. Cassini's view is this. It's a prolate spheroid. And what they did was, again, along two locations in France, one more northerly than the other, They surveyed the distances on the surface of the Earth. That would be D1 and D2. The angular distances, angle 1 and angle 2, were the same, but their surveying distances suggested that D1 was a little bit bigger than D2, and therefore the Earth had to be elongated at the poles. So it was a prolate spheroid. So for a while in the 1600s, we had these competing views of the shape of the Earth. And a little bit later, in the 1700s, the Académie Royale des Sciences, I can't even sound this. The Royal Academy of Science in France, to use the English version, set out to determine the true shape of the Earth once and for all. They actually set out two survey teams, one to Lapland, the other to Peru. And because they went farther north and farther south. After 10 years of surveying, in which they actually measured 1 degree of latitude in both places. And the Peru survey in particular was really, really good. And can you imagine in the 1700s going to either of those places and trying to very accurately determine a distance over a length of 100 kilometers? It's pretty incredible. Well, after they did this, the verdict was in and Newton was right. The Earth is an oblate spheroid.